So I think let's just start this 10. Like my plan for today is just finish up the whole chapter in one sitting. So we'll try to go through the whole chapter. It's a relatively shorter chapter. We finish out the chapter this week. I will do the lab next week. Then we can move on to the next chapter 10. So I'm not focusing on the mathematic parts on how to do the computation, especially for the polynomial kernel and the radial kernel. So I'll just focus on the general concepts. What's the support vector machines about? Okay, so that's the plan for today. So today we'll be just doing about, we first focus on binary classification models. Let's say we have two, whether you want to classify into like whether you have a disease or not have a disease. So we focus on the binary classification models using a maximal margin classifier. Then the second one, we also look at the binary classification model using a support vector classifier in the case where you want to allow for some misclassification. Then we can also look into binary classification models using support vector machines. Then after that, we want to generalize these support vector machines into multi-class cases. So what is a support vector machine? Support vector machine is just an approach for classification. And in particular, we focus on three things that you have to know by end of today is the maximal margin classifier, support vector classifier, and support vector machines. I will briefly go through the definition about what are all these. And so what the general one is, you can think of it like a maximal margin classifier and support vector classifier. I think they applies more for the linear class boundaries where you have a linear class boundaries, whereas support vector machine, it allows for non-linear situation. So it doesn't have to be, especially when you have multi-class. So this is more flexible way of doing it. So before we go into what is classifier, this maximum margin classifier, we have to understand what is a hyperplane. So hyperplanes, think of it is like a P-1 is a dimensional flat subspace of a P-dimensional space. So you can think of it like, let's say we have a binary outcome, then you have like maybe one dimensional. So you don't have a hyperplane where you just have a line. But if you have two dimensional, let's say you have two variables, x1, x2, then you still do not have a hyperplane. Your classifier will be more of a line. Then when you go up to three dimensional, let's say you have three variables, then you will have a hyperplane as a classifier. So this is just the way for like how they do hyperplanes. So it's a beta plus beta 1x and beta 2 equals 0. Then we use hyperplanes or lines if it's less than 2 dimensional, it's a line to classify. So think of it, you're like dividing it into areas. So let's say we have a binary classification, yes or no. So you want to put all the yes to one side of the line, then the no to the other side of the line. Okay, so you have like classified into two groups. How we usually classify, we call it Y, and you can call it either 1, Y equals to 1, or Y equals to -1. So it's one group or the other one. So this is an example of like figure. In the left part, you can see we have two classes of observations, either the blue dots or the purple dots. Okay, and this one is on 2-dimensional, so P2. And out of this P2, we have three separating hyperplanes. So it's because it's 2D, so most probably it's a line. Then on the right, you have these separating hyperplanes as shown in the black as well. Okay, then out of this, if you focus on the left side, you see we have 3 hyperplanes, but in the real situation, you might have more hyperplanes. And you can decide on what is the best hyperplanes. There are a few ways. One of it is we are talking about maximum margin classifier. So maximum margin classifier is just using a threshold. We can't have a threshold that gives us the largest margin to make the classification. So if you look on this left panel, right, they talk about we have this beta. Remember earlier this beta was equal to 0. So anything above 0, which is the blue part, we call it 1, y is equals to 1. Anything below the line is anything less than 0 is y equals to -1. Then we also want to consider something called the magnitude of this function. So if the magnitude is far away from 0, let's say this point at the end where it's far away from these hyperplanes, we can say that we are confident in its classification. But then when it's nearer to 0, okay, means nearer to the hyperplane, we are less confident about its misclassification. And why so? This is, we will talk about it, think of it when they have like points nearer. So they have similar features, so it will be harder for you to classify. So we'll talk about this as well as the misclassification with the misclassification later on. So maximum margin classifier. So I was thinking a figure would be better. So think of it this way, you have 2 classes, okay? Then you will have a margin. A margin is the shortest distance between the observations and the threshold. So these are the observations and the threshold. So those are like the margin. Maximum margin classifier is you want to use the largest margin. You want to use the largest margin to make the classification. So this you will have a maximum margin, and this is will be your hyperplane. So maximum margin hyperplane in the book definition is a hyperplane that is furthest away from the training data, and where we have this perpendicular, these are all the margins. So here, like the perpendicular distance to the threshold, they are usually the margin. Okay, what else did I miss? Wait, I forgot the diagram. Okay, so you can see this one, maximum margin classification. So the black line is the hyperplane. You have, these are the dotted, is the distance, the margin is anything between the dotted line to the solid line. Those are the margin. Then within the margin, or I would rather say on the line of the margin, right, the furthest away within the margin, you have 2 blue dots and then 1 purple dots. So these 2 blue dots and these purple dots, they are known as support vectors. So why they are called support vectors? They are called support vectors because if we change the location of this, we would have changed the hyperplane. Because hyperplane, remembers, is just the what you want to give the largest hyperplane. We decide hyperplane based on how we can get the largest margin. So imagine if you have, so this makes this max margin classifier, right, very sensitive to outliers. So if you have like very different points, your hyperplanes will have changed. Then what else? Okay, so if you can look at this like visual representation of maximum margin classification, one thing you have to remember is if we have changed the dots, right, the hyperplanes will change. So this means that your maximum margin classifier is very sensitive to outliers. Okay, and when you have outliers means, let's say this purple dots is over at this side. So it's very difficult for you to draw a linear hyperplane. So one way is maximum margin classifier is not really helpful in the case where you have observations that are like overlap, they might be in other classes. So one thing is we want to have a better model that allows for misclassification, one thing, and also we want to have a threshold, some kind of classifier that's like not sensitive to outliers. Because this is related to your bias and variance trade-off, right? So because here, if you look at the mathematics for the maximum margin classifier, we want to maximize the margin, and then we choose our beta to maximize our margin. So this one, the third equation, this one will ensure all our observations will be correctly classified as long as you have a positive margin. Okay, so before I go back to this, let's talk about this one. So various and bias trade-off, one of the thing is, let's say we have outliers. So this makes the maximum margin classifier is not an ideal threshold, right? Because we want some kind of model that allows for misclassification. So if we do not allow for any misclassifications, you will be like picking a threshold that's very sensitive to the training data, means like low bias, and then it will perform badly when we have new data coming in, which means high variances in your new data. But by allowing for misclassifications, we might have picked a threshold that's less sensitive to the training data, which is high bias, but it might have performed better with new data, which is a low variance. So this brings us to, instead of having a margin, we want something called a soft margin. Next. Okay, so we cannot always, we cannot always use a hyperplane to separate two classes and too sensitive. And so we want something called a soft margin classifier. What is a soft margin classifier? Soft margin classifier is you want to allow for some training data to be misclassified. So when we allow for these misclassifications, the distance between the observations and the threshold is what we call as the soft margin. So how we can have these methods called, we can use our cross validations to determine how many misclassifications and observations that you do want to allow inside that soft margin to get the best classification. So soft margin classifier is also known as the support vector classifier. So anything on the edge or within the soft margins, those are all support vectors. The mathematics part is still complicated. You want to maximize your margin as usual, but then now these times you have a C, which is a non-negative tuning parameter, which we have choose earlier. I said we can use cross validation to determine how many misclassifications and how many observations that you do want to be allowed inside that soft margin, right? Then the E's, the errors are those like slack variables that allow for your individual observations to be on the wrong side. So let's say you draw hyperplanes, then maybe few of the points will be on the wrong side. Okay. If your E is 0, let's say you have a 0 E. error 0. So means your observation is on the correct side of the margin, means correctly. Then if it's greater than 0, it's on the wrong side of the margin. Then if it's greater than 1, it just means it's on the wrong side of the hyperplane. Then, okay, let's talk about. So this is an interesting diagram. So if you look at, we have 4 figures. The hyperplanes are definitely different, but what we want to focus on these 4 diagrams is the margin. In fact, they are the soft margin. So think of it like this is the hyperplane. I'm talking about the diagram on the top left. So you have this hyperplane. So if we're using the maximum margin classifier, you would want all the blue to be above 0, means everything above that black line, black solid line. Then all the purple lines to be here. But as you can see from these hyperplanes, you have some misclassifications, as in these are the purple dots with the blue dots here as well, right? What is different among these 4 diagrams are the margin, the soft margin. Let's see here. What else do I need to talk about? So this 4 margin, as you can see on the top left, the margin is huge. Then the rest of 3 have like smaller margins. But here, when you have larger margin, you see that there's a high tolerance for your observations to being on the wrong side of the margin. But then when you have a smaller margin, when your C decreases, right, means the margin narrows down. The margin narrows down means there's a tolerance for your observations being on the wrong side of the margin also decreases. What else? So when you have all these classified, you want to remember that data points that lies or violate the margins will always affect the hyperplanes, especially all these outliers. So I've talked about bias, variance, trade-off. And when your C is small, you will have very low bias but high variance classifier. So it means you have a lower number of support vectors. Then they talk about logistic regressions we have covered previously. So logistic regressions and support vector classifier, in fact, they are very closely related. So logistic regressions, unlike the previous one, the linear discriminant analysis, logistic regression has a very low sensitivity to observations that's very far away from decision boundary. Then the next one is the support vector machine. Support vector machine is used to make when you want to make classifications, but then a lot of your classifications might not have a very clear linear decision boundaries. For example, one of it is dosage. So if you want to determine what's the amount of dosage to administer for, let's say, a cancer treatment, you wouldn't want to administer a very low dosage, which will not kill your cancerous cell, but you also do not want to administer a high dosage so that you kill all the healthy cells in your body. So you just want to administer an appropriate amount of dosage. So this one is a good example of why some situations, some decision boundaries are actually non-linear. So you have a range. So support vector machines is helpful as it allows you to compute in a high, you can start data in a relatively low dimension, then you can move a data to a high dimension. So one thing is we have two options like using the kernel. One is you can use these 2p features, which is referring to the polynomial kernel. So I skip the equations. So in support vector machines, you want to have enlarged feature space. So think of it, maybe it could be a linear, then you might want to make it into a quadratic, cubic, so a higher power. You can, like support vector machines, you can also include some of the interactive terms, higher degree polynomials, then your feature space will quickly enlarge and it will becomes very unmanageable computation. But the problem with support vector machines, they did not actually carry out the computation. So they did not actually transform the data. They just do something called the dot products to get the values without doing that computation, without transforming the data. So I think it's not covered in the book. Like they have all these equations, right? In summary, what they did in support vector machine is, let's say we start a data in a relatively low dimension. Let's say you can move from 1D dimensions into 2D. If you have one variables, then maybe I make it into a quadratic. Then you move the data into high dimensions. Then only we use similar approach like the support vector classifier. Then that will separate your high dimensional data into two groups. Okay, so then we have some support vector machines. They have something called the kernel functions. Kernel function is something that we can use, like systematically find a support vector classifier in higher dimensions in a systematic manner. So inner dots, also the dot products of observations, is where you just times the x of the lower dimension with the x with the higher dimension. Here. Then, so I find this very confusing. So like in polynomial kernel, like how I remember is like you have, let's say, two observations, you times the two observations plus with how do I say? You times the two observations, then you plus with the r to a degree of the polynomial. So that's how we transform it from a low dimensional relationship to a high dimensional relationship, which is this formula, but they're using x in the book. So we just two observations times up, then to a high degree of polynomial. We can also use, so when you're, let's say we have polynomial kernels usually has this parameter, which is d, as what we call as degree of polynomial. So you can think of it, when your d is 1, your polynomial kernel computes the relationship between each pair of observations. So you have all these observations and they draw the relationship between each pair of observations in one dimension. So when your d is 2, let's say you have 2 degree of polynomial, it just computes the two-dimensional relationship between each pair of relationship. So polynomial kernel will always, in a system, very systematic manner, increase your dimension by setting your d. And how do we actually decide it? How high do you want the polynomial kernel to go up to? That's how we use a cross validation. So to determine our D, means the degree of polynomial, we always want to use a cross validation. Let me see if I miss any points. I can try to cover this slowly. So what we want was the inner product, so the pairs of observation times out. Then the linear support vector classifier is as above, as follow, as in the function is always a beta. Then you have the alpha between the pairs of observations. Then here the functions. So K refers to the kernel functions. So they want to say you replace all the inner products with K to the pair of functions. This is the mathematic one. Then let's talk about radial kernel. Radial kernel is interesting, this one. So radial kernel is more like we using support vector classifier in infinite dimensions. So I try to look at the computation, but it got really, really complicated. But for my understanding is I feel radial kernel behave like KNN, the nearest neighbor, the weighted nearest neighbor models. So in other words means those closest observations, means the nearest neighbor, the observations that nearest, always have more influence on how we classify the new observation, let's say a new data, and observations that are further away have less influence on the classifications. So in radial kernel, the difference between the polynomial kernel and radial kernel is, in radial kernel, the differences between all your measurements, the pairs are usually square, means they always give you a square of distance between the two observations. So you have this distance between two observations and they are square. So in that way, because we are squaring it, the amount of influence of one observation has on the other is always a function of a square distance. Then in radial kernel, they are supposed to have this negative lambda. Okay, so given that you have a test observation X, let's say, and let's say it's very far from X, your kernel will be very small because you have a negative lambda and a large observations. Like so, this is the large distance between the observations. So your X will have very little, like very little role on the function. So all this is just the formula, but basic idea is observations that are nearer to the new data will always have more influence compared to the data that's far away observations have. So it's behave like KNN. So if you look at this diagram, right, you have left and right. The left panel is showing you a polynomial kernel with a 3 degree. 1, 2, 3. Yeah, 3 degree. And you have a non-linear data. Like think of it like the dosage, right? Like this will be low, then medium here. So you don't have a clear-cut hyperplane. So it doesn't make sense if you put the hyperplane here or here or here anyway. So you actually need like more of a support vector machine. So this is like 3. Here, we apply support vector machines with radial kernel, means the observations near one another are usually grouped. So why that? So for radial kernel, the feature space is always implicit and infinite dimensions. Let's go back to this formula. So here we have this gamma, right? So the question is always, how do we decide on what is the appropriate number for this gamma? So this gamma is what you can determine using a cross derivation, because the purpose is you always want us to scale, means you want to square the distance between these two. These are the distance, and you want to square it. So then by squaring it, we can also scale our influence. So gamma always scales your amount of influence two points have on one another. So whenever this gamma actually increases, your outcomes will actually reduce. That's why when the observations are far away from one another, they have less influence on one another. Then next one, let's say, is it possible, because we only talk about binary classes, whether yes or no. So is it possible to have a support vector machine with multi-classes, means more than two classes? Okay, so they have these two methods approach. One is one versus one approach, where you construct your kernel, combination of kernel over two methods, then support vector machines. K is your number of classes, how many classes that you have. Then all your observations will be classified to each of these combinations of how many K classes out of two classes. This time, previously when we have binary, we classify into either +1 or -1, right? So they say when you have K class, is always we can code it as +1 versus K class usually coded as -1. The other method is one versus all classification. So one versus all classifications, this is helpful when you have a lot of classes. So first you need to fit the K and one of the K classes to the remaining K minus 1 classes, means to the rest of the classes. Then you have to calculate the beta, because for hyperplane, our beta all we want it to be equal 0, then anything above 0 or below 0, that's how we classify. So this beta is always means the parameters that results from constructing and support vector machines, comparing the K classes coded as +1 to another classes as -1. Then we always assign, let's say you put in a new data, you want to check whether you put it into the class case where you want the beta, means your margin always to be the largest. That's how it works for the two classes. Oops, this is the lab. Okay, I think that's all that I have for. I really simplified the whole chapter, but do you guys have questions? Like for me, I find this one, like I think I saw one really good video on YouTube that talks about how they actually move from maximum margin classifier, where we have the maximum where we classify it based on the observations, then how they move it into the soft margin, which is the support vector classifier. Then from support vector classifier, we move into support vector machines. So those are like with diagrams. I saw one very good YouTube video, which I don't remember where, but it should be Josh Hammer something. That quest, I think. So if you look at it, right, I think I'll just paste in the chat. So if you look at the video, they actually talk about how we move from maximum margin classifier to support vector classifier to support vector machines. But the problem is that video is in, they're talking about things in Python. But I think the concept applies to all. Yeah. So I don't have much about
They even
vector.
have a song at the beginning.
I'm sorry. Can you repeat?
On the video, they even have a song at the beginning, so it's nice. By the way, my connection is super bad.
Yeah, your audio is cut off.
Thank you, Ling.
Yeah, I didn't
I'm sorry.
Also. Like, but for me, I roughly understand, but I just didn't like the mathematic part, so I skip off.
That's good. I have a question about there was a picture.
Yes,
like two pictures. Yeah, can you share your screen again?
Yes,
it's just I didn't understand that part. Maybe it's like good. There was two pictures. Yes, I suppose that one. You just showed it.
Number 9. Let's go one by one.
Okay. It was close to the last one, I suppose. There were two hyperplanes, and on the right side, there were like 3 circles. That I didn't understand that part.
That's because that's the set to the polynomial in the higher dimension. It's polynomial to degree of 3, I believe. Then the other one is using radial kernel. So they have 2 types of kernel. One is the polynomial kernel set up to degree of 3, I think. Then the other one is using radial kernel. This one, right?
Radial kernels. Yes. Now I understand. So, okay.
Yeah. So both are support vector machines. Okay. So, but this one is using polynomial kernel with a degree of 3. So this is a cubic polynomial. So this is cubic. Then they are both non-linear data, so they're using different kernel. This is polynomial kernel cubic. Then this one is radial kernel. So either both, the conclusion is like they're just using different kernel, but both seems to be able to capture the decision boundary quite well. Yes, here like within the soft margins, you can see like misclassifications here. This one would be like some, you did not fit in.
Yeah, but how about in the radial kernels? So in the middle one, we have the kernel. I suppose the solid one is the solid one kernel, and the dotted one.
Hyperplane. Yeah, this is the radial. Yeah.
So solid one was a radial hyperplane then.
On the right, on the right one is the radial one. This one. Yeah.
Okay.
This is how they classify things inside.
And the dotted circle, is it margin, or what does it mean on a radial kernel? The dotted line. What's that?
I think for radial kernel, right, because they are looking into infinite dimension, there's actually not really a margin, I think. I try to look at the calculation, but I don't think there's a really a margin like how we were thinking about it. Like it's not like clear margin like maximum margin.
I see.
What is that? Maximum margin, MMM.
Yeah. I recall that the soft margin is that a certain percentage of the data must be correctly classified, right?
Yes.
So maybe that's the circle. Maybe things inside the circle must be correctly classified. Like, yeah. So if you set your parameters like very demanding, like a very high percentage of the circle must be correctly classified, then the circle will be a lot bigger.
I think it makes more sense when we do the lab next week. But I thinking of the concept is like, yes, they running it because they running it a lot. Like what they did is like how you determine, let's say, why don't we just do a quadratic kernel, like, or do a like for polynomial you can do power 2, power 3, right? But the idea is that you compute all this, and what they did was a computer was like doing all this calculation for you, and they using cross validation. So they're using cross validation to determine what is the best kernel for you. Like you can run the radial kernel as well. Then you can compare whether is it better to use like to get the misclassifications, how many misclassifications that you get, then how many correct classifications that you have. So I don't think there's exact like a threshold like how many you want. So maybe you can have an idea of different one. Then you decide which one has more correct classifications, the model that have a higher prediction rate for classification. Someone posted. Oh,
Okay.
yeah, something
Thank you.
on chat. So my understanding of the radial one is, yes, 3 degree or higher dimension capabilities means it will be non-linear when it's plotted in a 2D domain. Yes. So how I understand is like when it's 1D, we transform the polynomial one is still like one line. But let's think of it like when you have 2D, it will be a line. Then when you have 3D, it will be the hyperplane. So as you go up, yeah, it will be like more non-linear. I think that's what I'm trying to say, right? The radial one is like 3D or higher. But when I was looking at the radial one, they say it's in the form of infinite dimension. So I don't think it's like 3D. I think it's like more than 3D. But then they are plotting it on the 2-dimension domain. That's true.
This is still a little bit confusing to me, but thank you so much.
Yeah, it's 3D plus. It's like really infinite. Like when I look at the math one, it looks very confusing. Yeah, but Nile, I think if it's like confusing for you, like because I started out very confused as well. So I buy the YouTube one, the one that I sent earlier. That one is really that one simplifies things a lot better. So if you watch that YouTube video first, then you go back and read the book, then everything just makes a lot more sense. Because I feel the book they cover a lot of things, but they didn't really like connect the ideas properly.
Okay, thank you.
Oh, thank you. Anyone else have questions? So I was thinking that I will cover slower like the lab next week, but I don't think we will take the full hour. I also want to try to do the tidy models for I have not done the lab yet. I'll try to see if it runs in my laptop. Okay, so I think we can end early today. So that's all. If you all have any other questions for me, you can post in the Slack group or send a message to me, or maybe for next week, if you have anything that you would like me to cover a bit more, slightly more than what covered in the textbook, please do let me know as well. I'll try my best to prepare for it over the weekend before we meet next week.
Okay, thank you.
All right, so bye.
See you next week.
See you guys next
Bye.
week.
See you.